they give you a definition as this. This is a joint distribution of n points on the real line. It's a one parameter generalization of the Gaussian orthogonal unitary and symplectic ensembles for the choices of beta 1, 2, 4. And there's lots of things known about it. There's effective probabilistic descriptions of the points themselves in many senses, in many scalings. But there's not really an effective way of describing its characteristic polynomial in general. So there's in the specific cases of beta is 2, there's lots of things that you can do. So the characteristic polynomial, there's no matrix here, but if it were a matrix, this would be the characteristic polynomial. It's just the product of z minus lambda I. There's a few things that we know about it. So probably the first thing that you could say is that this very well discussed log correlation exists in it. So this is the type of theorem that you could pull from existing literature, which is to say that if you look at the log modulus of the characteristic polynomial and you center it, then in various senses it will converge in distribution to a Gaussian process. And depending on what sense you want this convergence to have, this is either an easy statement or a hard statement or a proven statement or an unproven statement. The important part about the Gaussian is just that it has this correlation structure. So you have this 2 over beta log z minus y. And that is for z and y, which are between -2 and 2. The formula is different when you're up in the plane, for example. And then c is some continuous function. And if you can write much more precise formulas which hold everywhere. One way that you could actually formalize this sort of arrow with question marks around it or quotation marks around it, you could actually integrate this against test functions, and then this is a relatively straightforward theorem to prove that these integrals of this field against this test function converge to convergent distribution to that. Another way, which is maybe slightly more geometric, is if you actually look at the characteristic polynomial itself, well, that corresponds in this formula. I mean, you can realize it in this way by choosing this test function to be a Poisson kernel, and then you're getting that the convergence of this, it's not exactly the Poisson kernel, but something like a Poisson kernel, converges to G beta convolved with whatever that kernel would be. Okay, so why are we interested in the characteristic polynomial? Well, it's because of this chaos. So it's appeared a little bit. Let me just remind you. I'll just have a few slides about it. So the Gaussian multiplicative chaos is, in some sense, the exponential of that field in one dimension. So there's an extra parameter gamma that you could put here. I say equality here because you need to appropriately make sense of this. So it's not point-wise defined G beta on the slit between -2 and 2. So you should regularize it, and then you should appropriately renormalize. You take the exponential of the regularized object, you renormalize it, and you take a limit. And in that sense, you have equality. And this measure has nice multifractal properties. So there's a regime where it has those properties, which is the subcritical regime. And in this normalization, it would be where gamma over beta is less than 1. And there are some things known about the measure, for example, its dimension, and that it has some moments. There is a critical case when gamma over beta is equal to 1, and then you have a 0-dimensional non-atomic measure. And you can no longer take any moments of it. And then there's also a supercritical case, which, okay, it's maybe not clear if it's always canonically defined, but at the very least what it should be is a type of Poisson random measure, so you have a random collection of point masses of different weights corresponding to high points of something. So at a very basic mathematical level, we know that the log characteristic polynomial is converging in distribution to G beta. We know that lambda is this exponential of G beta. So we would like to say, well, does this hold? If you take exponentials before taking the limit, does it also converge to the GMC? And you can ask this question in reasonable ways in all the domains of gamma. The subcritical one is the one where this is most properly defined. You could also sort of ask it for gamma in the supercritical case. Well, okay, let me come to that. There's quite a bit of work on this now. There's a list of authors who have worked on actually proving versions of this, either in this Gaussian case or in the circular case. I don't think I'll go through everything. So we had Joseph talk about this paper, which is a great success for the circular beta ensemble. Recently, there has been also a big success by Claes, Foss, Lambert, and Webb for unitarily invariant ensembles. So that's GUE, for example. That's beta is equal to 2 in this situation, where they show convergence of this measure for all gamma less than the critical level. Sorry, was there? So there's still nothing in general beta, and that's in large part what I want to talk about. So I won't have a resolution of this statement for general beta, but I want to show some work in that direction. I just wanted to clarify what you could mean by convergence in the supercritical case. So in the supercritical case, the convergence on the previous slide is really encoding something about the extremal points of the field. And so at the very least, you would be able to extract from that information convergence of the maximum. And there is a very nice conjecture worked out by Jan Fyodorov and Nick Sim for exactly that convergence. And they explicitly characterize even what this X should be, which is a very fine piece of information, more detailed than the chaos would give. And in fact, the convergence of the chaos has other information. It's a sort of mixture of information about the extreme values. Okay. X is definitely related to the mass of the critical chaos. Yes, I don't know if that connection has been made. Was it made in some sense, or? Yeah. Okay. Okay, so I want to present to you some work on showing a way to actually effectively probabilistically describe the values of the characteristic polynomial of the Gaussian beta ensemble. There's a lot known about the eigenvalues, the zeros of the Gaussian characteristic polynomial, but somehow actually describing the values is a different problem. And the starting point for this description will be this random matrix. It's a tridiagonal random matrix. The eigenvalues of this matrix are distributed according to that Gaussian beta ensemble if you pick the B coefficients, or the B family down the middle, as independent normals, and if you pick the AIs as chi-distributed random variables with parameter beta times I. So that gives you a recurrence because this encodes a certain 3-term recurrence for a set of orthogonal polynomials, which will be random orthogonal polynomials. Now, it just comes from taking phi n to be the determinant of this matrix, Z identity minus it, and then cofactor expanding in the final column. And if you do that, you can encode the following recurrence, which relates phi n of Z and phi n minus 1 of Z to phi n minus 1 and phi n minus 2. If you call this Tn, then these are transfer matrices. They're not identical in any sense. They're sort of an evolving collection of transfer matrices, a smoothly evolving collection of transfer matrices. And this polynomial is then explicitly represented like this. Now, a really critical observation, which is very particular to this situation, not like, for example, the circular beta ensemble, is that the randomness here is very small in comparison to the mean of the transfer matrices. So n is the size of the matrix, B was a standard normal. So what we have here is, well, we have 1 over square root n times a normal. We have capital N terms if we go all the way out to the full size of the matrix. So it's in a type of diffusive scaling. The same thing holds here. You have a mean term, but then the fluctuations are uniformly diffusive across the recurrence. So this looks like a type of perturbation of a deterministic collection of transfer matrices by diffusively scaled noise. The exact theorem that I can share with you today is this one. This is not the theorem I would ultimately like to prove, but it's a way of describing that evolution of transfer matrices at points which are not particularly close to minus 1, 1, the support of the noise. It's the support of the spectrum. So what's going on here? We're actually going to build the probability space which contains those transfer matrices, and we're going to put on it the Gaussian field in such a way that this characteristic polynomial can be compared with, first of all, pi n of z. So I haven't defined it, but pi n of z is the solution of the deterministic transfer matrix recurrence, and it's actually just an Hermite polynomial. So it's the Hermite polynomial, which is appropriately defined, or appropriately scaled. Mu beta is a smooth mean term, which is explicit, but I haven't written it. And finally, G beta is a smooth Gaussian field, which is blowing up logarithmically as you approach the support of the spectrum. Okay, the domain, I can say what it is. It's just something that looks like this. I can't remember if I put it between minus 2 and 2 and 1, so let's put it like this. The approximation holds on the complement of this region, and this width here is n to the minus 2/3 times log n to the 2/3. Is it 2/3? I think it's actually 1/3. And then this one is n to the minus delta. It's not particularly close here. It is pretty close here. And in fact, if you tried to make it closer, you would need to start incorporating new effects, which are not just Gaussian. You would need to have something else. Delta is a fixed parameter. You cannot take it close to 1. It's less than a half, I think. Okay. So, by the way, this is Gauthier Lambert with whom this is joint work. Okay, so the principal thing I'd like to describe to you is how to say something interesting about this transfer matrix recurrence, which is a type of perturbation around a well-known transfer matrix recurrence. So the well-known transfer matrix recurrence is this Tn tilde, which is expectation Tn. These are the matrices. These are in fact encoding the actual recurrence for Hermite polynomials. So in principle, you have everything that you'd like to say about them. In fact, there's the weight for people who are particularly interested in what the orthogonal polynomials are. There's a change in behavior in this transfer matrix recurrence. So as you look through the recurrence, these are changing as you go, you actually see three sort of distinct phases of the deterministic recurrence, and that affects what happens to the perturbed one. Okay, so first of all, this is the noisy version. You can write Tn as I was saying, a diffusive perturbation of that one. To see the change in phase of the deterministic matrix, it's most useful to look at its eigenvalues. So this is just a nice simple 2x2 problem. Very straightforward. These are explicitly the eigenvalues. The change in behavior happens, of course, when this square root goes from being real to being negative. And in fact, more than that, if you actually were to put in 0 here, so that lambda plus is equal to lambda minus, this equation is nonsense, and it's because the transfer matrices cease to be diagonalizable at that moment. And that's very important because we're going to perturb this. So if they're not very diagonalizable, that is, they're far in a quantitative sense from being diagonalizable, then the perturbation is going to be bad too. So in a window around the place where this becomes 0, you need to do something different. So I'm going to give you a threefold way. That's a cheeky name. It's not the actual threefold way. It's a different threefold way. So here are the threefolds. You can have either the three cases of the signs. And this is, I think, just repeating what I was just saying. So you have the cases where that thing inside the square root was positive. You have one eigenvalue larger than the other and real. In the other case, you have complex conjugate pairs, and in the middle, you have something non-diagonalizable. So I think it's helpful to think of this as a geometric problem, maybe. The section that I'm going to focus on, or where that theorem comes from, the theorem that I presented to you, is by studying this problem, which is the hyperbolic portion. So that's the portion where you have where you have real eigenvalues of separated modulus. The first case. And I've drawn a simulation here for you. So what's going on in the simulation? So you can identify 2x2 matrices with matrices with isometries of the hyperbolic plane here after removing the determinant, which is a simple operation. And for simplicity, I've taken the one such hyperbolic matrix. So what does it do? It fixes a point on the boundary of the hyperbolic plane, and it pushes things towards it. So if you just took the deterministic matrix, you would see this gray trace going on below. That would be the orbit of a single point under iterated applications of this deterministic matrix. Around it, I put a perturbation in diffusive scaling. And the most important thing, I suppose, about this is that it respects the fixed point. So the perturbed orbit still tends towards this point up here. It gets pretty messy as you get close, and I don't actually know if that's what exactly is going on there or if it's a simulation effect. But it still goes there, and in fact you can say a lot more about how it goes there. The bottom line is that the perturbations cause a very tiny bit of variation around the orbit. Most of the effect of the perturbation is in where you lie on the direction of the orbit. In the case that you have non-diagonalizable. The boundary case, you would have a parabolic transformation. So that's something that in this picture would take a point and let it flow along a circle which is tangent to the boundary of the plane. And this is again the same scaling. So I won't have so much to say about this picture. I put it here for comparison. And then finally in the complex conjugate pair situation, the eigenvalues become conjugate pairs. So what you see is in fact a rotation. And so the orbit would rotate around it, and in fact the perturbed orbit does something like it as well. Okay. So that's a little picture. And I hope that kind of the argument I wanted to make by showing these pictures is that there's actually 3 problems to do here. In each of the 3 situations, you have an underlying deterministic dynamics. You're adding a perturbation to it, a random perturbation to it. In each of the 3 situations, you're going to have a different response. So what does that mean for the original problem? Well, the characteristic polynomial can just be factorized into the 3 portions corresponding to where in the evolution you are. You're going to have a hyperbolic region. You'll have some sort of parabolic region, and finally you'll have an elliptic region. And in each of the 3, you need to formulate a sort of separate result. So here's where I have the most to say. I can tell you a little bit about what we think happens in the parabolic section, and also what we think happens in the elliptic section. Okay. There's a width parameter here, which is a little bit arbitrary. So strictly speaking, I mean, the parabolic, you only fail to be diagonalizable in the deterministic problem at a single point. But that somehow doesn't reflect what's actually going on. So we have to fatten it, and this is how much we fatten it by. It is meaningful. It's not just for technical reasons that we choose these things. The end of the 1/3 is the familiar scaling from the Airy equation. If you went out multiples of n to the 1/3, you would sort of be seeing a fixed set of time in the Airy time. Log n to the 2/3 is because that's how far out in the Airy tail you can go before the Airy tail starts to decay to powers of n, which is important because we're perturbing by things which are on the order of powers of n. So this is, I think, basically is the best you could hope for. If you tried to make it smaller, it would be wrong somehow. Okay. And that leads to our definitions of hyperbolic, parabolic, and elliptic, which are now just the original definitions, but fattened up by this amount. Okay. Oh yeah, and just I think I said it once, but I want to emphasize for this theorem, that is to approximate the characteristic polynomial in these points in the plane, where you're outside of this box. The significance of it is that, in fact, these portions don't appear in the recurrence at all. So you really can just understand the characteristic polynomial by the hyperbolic part of the recurrence. It's also true, for example, that if you wanted to say something about the characteristic polynomial near the edge, in a window around the edge, you would just need to understand these two, the hyperbolic part and the parabolic part, the Airy part. However, if you wanted to understand the characteristic polynomial in the middle, maybe counterintuitively, you would need to understand all 3, including the Airy part of the behavior, which doesn't actually appear in any general random matrix theory asymptotics for what happens in the bulk. But somehow for the characteristic polynomial, it's still important that you have an Airy component. Okay. So I want to describe a little bit how what you actually need to say to answer something about this hyperbolic part of the recurrence and why it's possible. So the deterministic matrix can be expressed in its diagonalization like this. And in the hyperbolic part, lambda plus is bigger than lambda minus. So I just want to reframe this problem a little bit. So here I've algebraically done nothing. I've just inserted these v's inside there. So this is really the same as this. I just put a v3 next to a v3 inverse, and I did it everywhere. If you group these terms, what's going on? Well, v3 inverse is not exactly the inverse of v2. This is close to being a diagonalization. It's a little bit off. But each of these is close to being diagonal. And in fact, you can compute how close they are to the diagonal. And it has everything to do with how close you are to the turning point where the Airy asymptotic occurs. So if you just define some etas just to be some random variables, which are whatever's left over after you extract the diagonal part of this, then you have the following situation. If you call this matrix UK, we have the product of UKs, and I want to claim to you that the correct asymptotic for the product of those UKs is just matrix 1, 0, 0, 0. If you succeed in showing that, then you can say everything you would like about the resulting hyperbolic part. So why is there any chance that this is 1, 0, 0, 0? This is what I was just saying. So the toy problem is the following. You would like to take the product of matrices that looks like this. You have 1 and then some entry which is less than 1. And then you have some kind of perturbations here. And what you would like to do is compare this, this product of matrices to the same product where you just have the diagonal entries of it. So how does the hyperbolicity help you? Well, if you were to just work out what would happen as you took just a brutal expansion in terms of how many times you use an eta. So you could imagine taking terms where you go from 1 to 1, and then you use eta. When you use eta, you end up in a different location in the product. You could then sit here and do 0.9 a couple times and then go back. Well, if you just compute, the important thing is that it's expensive in these products to stay here at 2 for too long. Because as you take more and more 0.9s, you're decaying exponentially in the number of terms. So, for example, if you wanted to understand how far off you are in the first entry by just dropping the etas, well, you have to take some products here, and at some point you'll go over here using an eta, then you stay here for a while and you go back. So you go forward and you go backward, and you basically have to go forward and backward at the same time. Because if you spend too long, the 0.9s start to add up and you have exponential decay. So there's n choices of when you can go over, and then you have to go back immediately, and you end up with some kind of error which is like n times eta squared. Which is a lot better than what you would do if you tried to just use, say, a norm argument. Then you would lose an eta for each term, and you'd have n of them. So it'd be n times eta. So it's a factor of eta better than that. Now, that turns out not to be good enough for our purposes, because you can still get more. This is not correct for random things, because in our situation, those matrices are independent. They're diffusively scaled. So the fluctuating part, you have to take advantage of that. So if eta corresponds to the magnitude of the fluctuating part, then you would have n times to go over. You have to use it twice. But then if they were centered random variables, you would end up with a variance of n times eta to the 4th. So it's down another factor. Okay, so this is an interesting heuristic. I don't know how to implement this as an argument. So the argument is actually much different than this. It has to use norms in an appropriate way, but it does produce the right prediction. Okay. So that more or less is the key to making the hyperbolic part work. Let me also share with you what we now think happens in the parabolic part. And I don't know how to use the transfer matrices to make that work, but here's the prediction. So if you look at the three-term recurrence, which is just encoded by this transfer matrices, then near the turning point, near the point where this is becoming parabolic, the key thing is that this coefficient and this coefficient are roughly the same, and the z is appropriately chosen to be about -2. So in fact, this is looking like something like a discrete second derivative. And if you work out what's left over, you have that this second derivative in n is approximately some kind of whatever this is, some fluctuating part, some factor of 1 over n, and then phi n. So if you were to pass to a scaling limit of that, this is becoming a second derivative, and you're going to get this equation. So psi double prime is minus g plus dzt, an increment of some complex, real Brownian motion, excuse me, times psi. Okay. So this equation is the stochastic Airy equation. And you need to make sure that you match boundary conditions of it, which is the hardest thing to do with it. Here I've drawn a rendering of it. Now this is going the opposite direction that the Airy function usually goes. Blue is the Airy function, and green is the stochastic Airy function. It's actually, in some sense, important if you want to view this in any kind of Ito sense to run it in this direction. The stochastic Airy function, that is, and that's the same direction that you get from the actual recurrence in the transfer matrices. Because you go from small to large, that corresponds in time of the Airy function of going this way. And just, you can see that it's doing something like Airy, but it has some sort of fluctuations. It's interesting as a question to ask if stochastic Airy has the same type of decay properties as Airy. This is an open question. For example, we know that Airy decays like a power of t. Is it also true that stochastic Airy decays? Maybe not clear from this picture. And I think that what's expected is that it should decay like a power of t, but it should be beta dependent. Okay. By the way, beta was not visible here, but beta appears as a scaling factor in front of dz. Okay, I'll also just show a log plot of what goes to the left. So this is to emphasize that in fact the decaying part of stochastic Airy is actually, it's easier to say things about and matches Airy very well. Okay. And I have just one more slide, which is the elliptic part. So this is the portion of the transfer matrix recurrence where really non-Gaussian things happen. And this corresponds to what goes on in the bulk. So the portion of the recurrence which is now actually telling you where eigenvalues are. So we conjecture this is the case, that you can, like in the previous theorem, build a probability space which supports the transfer matrices, and also some continuum evolution, some stochastic diffusion, so that these all go to 0, and I can show you what the diffusion should be. It looks like this creature. It's a 2x2 matrix evolution, which encodes inside of it this stochastic sine equation with which some of you may be familiar, though it's a little bit tortuous to extract it. But it's a matrix generalization of it. I don't know if I have so much to say about it, but in any case, this is what the behavior should be for the actual transfer matrix recurrence in the bulk. And this I think is where I decided to end. So if there are any questions, I'm happy to take them.